Alrighty, so I'm going to go through some quick notes with you as homework, talking about entropy and spontaneity, just the very first part of Learning Target 2.5. So it says we're going to use Gibbs free energy, which we're not even going to touch today, to determine if a process is spontaneous at a given temperature, and explain how entropy affects a process's ability to be spontaneous. So first we're going to talk about reaction spontaneity and what it means for a process or a reaction to be spontaneous. So for a process or a reaction to be spontaneous, it has to be one that, once it begins, continues to completion without outside intervention. So I'm just looking at some of my many grammar errors here, but it's something that once you start it, it's going to keep going without there having to be anything to prompt it to move along. So for example, if you were to take a rock and put it on top of your desk, and that rock were to be pushed off your desk, the process of the rock falling is spontaneous, because once that rock gets off the table, it is going to continue to fall without you having to do anything about it. So that would be considered a spontaneous process. A reaction is the same way. Like, once it gets going, it is going to go on to completion without having to have some kind of outside force act on it. And just because something is spontaneous does not have anything to do with its speed. So it is not the same as its rate. So you can have a spontaneous process that is very, very slow, and it is still considered spontaneous. So just because it does so very slowly does not have anything to do with the fact that it's spontaneous or not. A spontaneous process can be very quick or very slow, but the main thing is that it's going to do its thing to completion without anything having to act upon it. So what we're going to do is use some different variables to decide if a process is or is not going to be spontaneous at a given temperature. And to discuss that, we need to talk about a new term, which is called entropy. And entropy is simply a measure of the amount of disorder in a system relative to something else. So entropy is this amount of disorder in a system. So a really easy way to think about this is a package of markers. So picture the little skinny markers that I put out on your desk sometimes. And they're all 8, nice and neat in their box. And you brush it with your elbow and the box falls out into the floor and all the markers go spilling everywhere. What you have done is increased the amount of disorder in that system. So you went from a relatively ordered state to a relatively disordered state. So the amount of disorder has increased. Think about your room. Your room at home, I would guess, tends to a state of disorder. So you can clean your room. At least this is how my house works anyways. You can clean your room or your house or whatever. And that room is going to tend to become more disorderly over time. So the entropy is going to increase of that system. Now, when you go through the process of cleaning up your room, you decrease the entropy because you decrease the amount of disorder. You make it more nice and neat. So these standard entropies we can assign to a system, but they're all relative. We can't measure the actual entropy. We just measure them relative to each other. So this all applies to the second law of thermodynamics. The first little star there is the actual book definition, and the second is me trying to explain it better. So the second law of thermodynamics says the entropy of the universe, remember the universe is the system and the surroundings together, the entropy of the universe increases during any spontaneous process. So the entropy of the universe must increase during any spontaneous process. And in fact, I'm going to go ahead and just remind you that the universe includes both the system and the surroundings. So we would need to take into account the entropy of both and how they're related. And the second little star there is me trying to explain it. So energy is going to try to disperse from being concentrated to spread out. So if you think about a lot of just normal everyday things. Like think about a hot pan on the stove. If you take the hot pan off the stove, that heat is going to tend to dissipate. Energy tries to disperse from being concentrated to spread out. Same thing if you wind up a spring, it's going to spring out until all that potential energy is gone. So the entropy of the entire universe, that amount of disorder, is going to tend to increase if it's going to be spontaneous. So if that process is going to continue to completion without outside intervention, it's going to have to increase the entropy of the universe when all is said and done. It's kind of an out there thing, but we're going to keep talking about it. So let's talk about delta S. So if you were to look at the entropy of a process, you would want it to measure its delta S. So delta S would be the change in entropy. So if your delta S was positive, that means you would have the final entropy minus the initial entropy would be positive, meaning that you have more disorder when all is said and done. And remember, this applies to your system. If delta S is negative, then you're going to have the opposite thing going on. S final is going to have a lower entropy, which means you're going to have less disorder as a result of that process. So we want to talk about how this applies to some basic processes. For example, if we have a change in state. So let's say we have water, and we're going to have some melting water. Now, if I just look at the fact that water is going from a solid to a liquid, water as a solid is more ordered than water liquid because those molecules are not as in a nice, neat structure. They're more spread out. They're moving around more. They have more energy. They're kind of haphazard. So, excuse me, I'm going to change this so it says more disorder over here and less disorder, which is the same as more order, but you can get yourself really confused. I always just stick to the disorder term. So if I go from less to more, that means your delta S, that's a terrible S, your delta S is increasing. You have more disorder. Now let's say you were going from steam and it's condensing to a liquid. The gas has more disorder, and gas is the trump card of entropy. Gas is always the most disordered state. So in this case, we're going from a more disordered to a less disordered state, so our delta S would be negative. So you can apply that to changes of state. Now we have some examples of changes in entropy when it comes to dissolving things. So if I was going to take a solid, such as salt, and make it aqueous, that's going to go from a nice, neat crystal structure, so less disorder, to more disorder, because now it's flopping around in the water. So delta S of a solid that's dissolving in a liquid, so you're mixing these two things together. Here I had this nice, pure, crystal, orderly salt, and now it's all mixed around with water. Then the disorder is going to increase. Now for a gas in a liquid, remember, like we have something like HCl, and that's going to become hydrochloric acid. Gas is trump, so this is the most disordered state that you can have. So you're trapping that gas. It was free to bop around and do whatever it wants. Now it's kind of trapped and confined in the liquid. Delta S is now going to be negative because it's losing disorder. It's becoming more orderly by being trapped in that water. And then anytime you have a same and a same, like let's say you have hydrogen peroxide. My handwriting is getting terrible here. I apologize. So you have hydrogen peroxide liquid, and you're going to dissolve it in water, so it's going to become aqueous. So same in a same means like the same state, like a liquid in a liquid, or a solid in a solid, or gas in a gas. You go from one pure substance, so in this case nice and pure hydrogen peroxide, to more disordered because now you've got two substances all mixed up. So anytime you have a same in a same, so same state mixed into a same state, your delta S is going to be positive. And the final thing you can do to predict changes in entropy is look at the number of gases used in the reactants versus gases created in the products. So that would be moles of gas. So for example, let's say that we're going to take some glucose, which is a solid, and we're going to react it with 6 moles of oxygen gas. And because we know that this is respiration, we know that we're going to make 6 moles of CO2 gas and 6 moles of water vapor. And so if I look at this equation, just based on the sense that there's only 6 moles of gas over here versus 12 over here, this is going to have more disorder simply because you end up with more of the gas than you started with. And gas is, remember, the trump card when it comes to disorder. So we could predict that this reaction would have a positive delta S. So that's just some things to think about, and we're going to do some more specifics in class, but I wanted you to get those down just so you can start to think about entropy and disorder and spontaneity, and we can dig into that a little further. So thanks for hanging in with me, and we will talk about this more very soon. Thanks.